This video begins by introducing the concept of a straight line and a formula which can represent it. Now, straight line equations are used in every discipline you come across, so that could be engineering or nursing, finance or history, and almost anything you could name. And consequently, this is very important, a good feel for how to interpret and handle straight line graphs is essential for many normal day-to-day jobs. So this video is going to give a simple introduction to the straight line graph. Now, before we do that, we need to make sure you know how to represent data on a graph. We're going to assume that you can, so this is just a quick reminder. So let's assume we want to place some coordinates on a piece of graph paper, and what we're going to do is represent the number of games won or lost versus profit or loss. So the horizontal axis is going to be the number of games, and the vertical axis is going to be the profit or loss, where a negative number is a loss. And as with the games, a negative number with games means you lost the game. So the coordinates we're going to give you are as follows. We might give you coordinates something like 1, 4. Now, because we've said the horizontal axis is the number of games, and you always take the horizontal axis first, that means these coordinates represent 1 game, and the 4 means you made a profit of 4. I've also given you some other coordinates here. Now, we're going to give some graph paper, and we want you to mark these coordinates on the graph paper. And remember, you always give the horizontal coordinate first. So here's the graph paper. So we'll start with the 1, 4. So you remember, you take the 1 first, there's 1 on the horizontal axis, and you pair that with 4 on the vertical axis. There's 4 on the vertical axis. So if I put those two together, there's the coordinate 1, 4. Now I use a different colour for the next one. What about the coordinate 2, 5? I take 2 on the horizontal axis, I take 5 on the vertical axis, put those together, and I get this point here. What about -3, -4? Well, -3 comes first, so I take -3 on the horizontal axis, -4 on the vertical axis, and that gives me this point here. And I'll have to go back to blue because I've only got 3 colours for the last one. -5, -2. So I take -5 on the horizontal axis, -2 on the vertical axis, and that gives me a point just there. So there's my 4 points. Okay. Now what we've done is we've given you some data. Now this is fictitious data based on beef consumption, should we say, in the UK, and you'll see it's the consumption of beef given as kilograms per 1,000 persons per year. And we're looking at how consumption changes through time. So you'll see we've given the years down here. We've started at the year 1860 and we've gone all the way up to the year 1980. And the first thing is that if somebody gives you a piece of graph like this, you should be able to interpret it. So for example, if I said to you, what was the consumption in 1950? I'd expect you to say, okay, there's the year 1950. So I can follow this line up to find my point. There's my point. And you can see the consumption in 1950 was 1,960 kilograms per 1,000 persons per year. Now here's some questions. Is there an obvious trend in this data? Well, hopefully you can see there is an obvious trend. It seems to be increasing. But can we be a bit more precise? Is it increasing, or is it doing more than increasing? And I think it would be fair to say you can see it's pretty much a straight line. So what I can do, it's difficult to draw on the screen, but I'll do my best. You can see that you've pretty much got a straight line graph going through those points. Okay? Now, having noticed that, how would you estimate the consumption of beef in the year 2000? You'll notice our graph only goes up to 1980. So how could you estimate the consumption in the year 2000? And that would be very useful for a business person or a shopkeeper or somebody of that nature. So what we can do is, you've seen how we've drawn this straight line. All we need to do is extend this straight line up to the year 2000. So there we go. You'll see we've extended the horizontal axis down here to include the year 2000, and we've drawn the straight line, and it's taken us up to this point here. Okay, once we've got that point, so we've found the year 2000, there it is marked with the arrow, and then we can find the corresponding kilograms. There it is. It's about, if I write it, 2010 kilograms. However, there's a bit of an issue here. What you'll notice is I've done these things by hand, and so this is approximate. And it depends on how accurately we sketch the graph and how well we can estimate values from this. Here's a different example, taken from a hospital. A drip delivers 4 millilitres per minute to a patient. Now, given the initial volume in the bag is 1 litre, sketch the volume remaining as a function of time. So you'll see at time 0, there it is, we start with 1,000 millilitres in the bag, or 1 litre. And then we're going to lose 4 millilitres every minute. So you'll see we've plotted all these crosses to show how the volume reduces with time. Here's the question, is there an obvious trend? Well, clearly there is one trend. The volume in the bag is getting less, as you would expect, with time. And what would this trend be called? Well, again, hopefully it's obvious, looking at these crosses, that you can pretty much say this is following a straight line. Okay? So how would you estimate the time the drip needs changing? So if you're a nurse on a ward, you've put the drip up, you want to know, when is this going to be close to empty? Because that's when I need to change it. So how are you going to do that? At the moment, we've got to 100 minutes, you can see here, and the drip has still got 600 millilitres left in it. So we're going to do the same trick we did before. We're going to draw this straight line, and we're going to extend it until we get the drip empty. There we go then. You'll see I've extended the time axis as far as I need to. As it happens in this case, it's around 250 minutes, and we've extended the volume axis so that we get to 0 volume. And what do you notice? You get to 0 volume in about 250 minutes. So those are the steps. Find where the volume equals 0, find the corresponding time. Okay, but again, what you'll know is this is approximate, because in practice, if you're doing this on pen and paper, you're not going to be quite as accurate as I was here. And so depending on how accurately you sketch your graph, and therefore how well you can estimate values, your number might be there or thereabouts, but it's unlikely to be exact. Here's a key question, just to make you think. Why is this useful? When would you replace the drip? Well, I suggest you're going to replace the drip when it gets to somewhere around here, around 100, just to be on the safe side. And so that's roughly the time that you'd be looking for. So what are the issues? It's clear that many real behaviours that you're going to come across in everyday life can be represented by straight lines on graphs. However, sketching these by hand is tedious. If you had to sketch all these different crosses and draw straight lines, you'd soon get rather bored. Estimating values from them is prone to error due to the inaccuracies of human sketching. And it's not easy to automate using computing, and increasingly we want to do all these things on computing. Consequently, we need some tools to make this process more efficient, more accurate, and ultimately we want to automate it so we as a human aren't doing tedious jobs that we're not very good at. So here's a different example. You're a shopkeeper. You're charging 35 pence per apple. And you want to know how much to charge if you have 1, 2, 3 and so on, up to 20 apples. Now, the tedious thing to do is to first of all produce a table like this. You see, if I've got 1 apple, the cost is 35. If I've got 2 apples, the cost is 70. 3 apples, 105. 4 apples, 140. 5 apples, 175, and so on. And you see, I'm soon getting bored going all the way up to 20 apples, and especially if I owned a veg shop and I had to do this for every single thing that I was selling. Okay, I could then draw a diagram like this. You'll see I've marked all the different values, so you can see if I had 2 apples, the cost was 70. Now, this is somewhat tedious, so what we want to do is find out, is there a quicker way of representing and calculating this information? And one of the things we might want to use is the gradient. What is the gradient of this curve, and what does the gradient mean? Well, basically it means how much I go up for each one along. So you can see if I go along 1, I've gone up 35. If I go up 2, I've gone up 70. If I go up 3, I've gone up 105. So here the gradient is 35, because I go up 35 for every 1 I go along. Now, why is that useful? We could have said that the cost is given by a very simple formula. Here it is: the number of apples that you've bought multiplied by the cost per apple. Now, as it happens, this formula is the equation of a straight line whose gradient is the cost per apple. And what was the cost per apple? It was 35, and the other thing about this equation is it goes through the origin. So you'll find we've got an equation here: cost equals number of apples times cost per apple, which represents the data on our graph. So rather than producing the whole graph, all we need to do is remember we've got this formula. Okay, let's try some other examples. So which formula, and hence which straight line graph, would represent the following scenarios, and what are the gradients? So number 1, in a training exercise, a student uses 50 calories per circuit. Represent the outcome of doing numerous circuits. So in other words, how many calories are they using in total? Or number 2, a car does 40 miles per gallon. Represent the total mileage that can be covered based upon the amount of fuel in the tank. So we'll go to the next slides and we'll look at the solutions to these two. So first, in a training exercise, a student uses 50 calories per circuit. Represent the outcome of doing numerous circuits. So first, I'm going to write down here how many circuits they've done. So they might have done 1 or 2 or 3 or 4 or 5. And then on the vertical axis, I'm going to use calories. So if they do 1 circuit, they've used 50 calories. If they do 2 circuits, 100 calories, 3 circuits, 150, and so on. And you can see I can mark all these crosses, and very quickly you'll notice there's a straight line here. Okay? However, is there a formula here? Well, there is, because what I'm actually writing is calories equals 50 times number of circuits. So you've actually got a formula which represents this data. The gradient is given by this 50, the vertical axis given by calories, the horizontal axis by number of circuits. So this formula represents this graph. Okay. Second one, a car does 40 miles per gallon. Represent the total mileage that can be covered based on the amount of fuel in the tank. So again, I could put down here on the horizontal axis the number of gallons of fuel that we've got. So I can have 1 or 2 or 3 or 4 or 5, 6 and so on. If I have 1 gallon, I can do 40 miles. 2 gallons, 80 miles. 3 gallons, 120. 4 gallons, 160, and so on. So what I've done is, again, I've marked lots of crosses to show what the mileage would be. And again, I can form a straight line that goes through all these points. So what's the formula that I've used here? Well, hopefully it's obvious. What you've written is mileage equals 40 times gallons. So your gradient is 40 and your formula is mileage equals gradient times gallons. So again, you see there's a simple link between a formula for a straight line and the data that you could have produced easily just using common sense. What about a generic solution? Here's a straight line here. Can you find a formula which represents this straight line? Well, first of all, let's mark some values for the horizontal axis. So I'm going to put 1, 2, 3, 4, 5, and so on. Next, mark some values on the vertical axis. Okay, so 1, 2, 3, 4, 5, 6, and so on. Now, can I work out the gradient? Hopefully it's obvious to you here that the gradient is 2.5. You can see if I've gone along 1, then I've gone up by 2.5. So the gradient is 2.5. So what this means is I can now write that the vertical coordinate, excuse my spelling, is equal to 2.5 times the horizontal coordinate. So I've got a simple line, and quickly I've gone from that line to a formula which represents that line, which is the formula for the straight line. Okay, and that's reiterated there. So the vertical coordinate is the gradient times the horizontal coordinate. So in summary, we've introduced the concept of straight line graphs. We've shown that some of these can be represented by a simple formula of the following type. The vertical coordinate equals the gradient times the horizontal coordinate. We've indicated that such formula represent many real scenarios.